so as I was saying, thank you very much, Giuliano. I just going to wrap up very briefly the discussion of soft gluon emissions and then start to actually do a calculation where you want to show an accurate calculation for a Risson distribution. So yesterday what we did is that we considered like an amplitude with n hard directions labeled by Q1 to Qn, and then maybe plus some later weak stuff if you think about our Drelian process, and then we consider the emission of a soft gluon with momentum k, and we derived essentially this Eichmann factor. So we showed that there is some factorization at the level of the amplitude, but the factorization is not complete because the QCD vertices also, well, they depend on the color matrix, which gets trapped between the reduced matrix element and bar and the spin. One interesting thing is that if you did the calculation for a gluon line, emitting a gluon, you will find a very similar structure. So this Eichmann factor is actually the same for emission of a gluon line or of a quark line. And the way we say is that the Eichmann factor is independent on this, does not depend on the spin of the emitter, and you only get it if you emit the spin 1 part. Of course, for a gluon, because of gluon emission here, you won't have the Gelman matrix TA, but you'll have FABC structure constant. Okay, so as I said, I'm not going to give details which are in the notes, but what you want to do next is you want to sum over all possible emissions, so from every possible leg. There's a subtlety when you emit from the initial state leg, the incoming leg, there is a minus sign difference, which you can treat it as a different sign in the I epsilon prescription. And once you have sum over all possible ways the soft gluon can be emitted, you square the result and you sum and average of the polarization external quantum numbers of the external lens. Two important things. We can show that you get this soft enhancement only if you emit off external legs. You need on-shell particles. And another thing which is not difficult to see is that when you sum, so what we want to do is that we want to sum over I, okay, because the gluon can be emitted of any leg, and then we square it and we take the average or the sum over the external quantum. When you do that, you see that because the external particles are massless, the only term that survive are actually the interference terms. So whenever you have say M3 times M3 star, you get 0 essentially because the this epsilon mu times epsilon star mu times epsilon nu, when you sum over the external state polarization, you get a minus G mu, and so you'll have, when you contract this, you'll get QI squared, which is 0. And so only the interference terms survive in the soft limit, which is very different compared to the collinear limit, where we essentially looked at the semi-classical approximation. Soft emission are really tied up with the quantum mechanical effects. So what you get here, if you do this, is that you get, okay, you have alpha s, j squared, so 1 power of alpha s. And then you're summing over I, all possible I and j, qi dot qj, qi dot k, qj dot k. And this is the square of the Eichmann factor. And you see here that if you pick I equals j, and then you'll have to deal with these, squaring this complicated structure. Here, I would say that the most powerful way of dealing with that is to use a more abstract color notation. This was developed, for instance, by Stefano Catania and collaborators. And one way we can write it is that essentially what we have are some abstract color operators, Cij, which can be presented, for instance, by matrices if you fix the basis. And you have to take matrix elements of these color operators between vector states. And these vector states, the states M, are vectors in color space. And they're such that, for instance, that if you pick Ci, this if operator Cij is proportional to the identity, then M is nothing but the matrix Riemann square. Okay, so for instance, in QED, where the gauge group is abelian, all theseCij's are proportional to the identity, and so you have a full factorization in the Eichmann limit. In QCD, you still have an Eichmann factor, but then you have to evaluate these rather complicated color matrices that comes with these formulas. This is a fairly famous formula. It's known by its name. Is for instance, you can call it the sum of a dipole formula, because you can consider the gluon as emitted from each dipole ij, and then you have to sum over all possible dipole ij's. So I already said that if the group is abelian, then all this matrix structure is trivial. Actually, what you can show, and is done in the notes, well, some of it is done in the notes, some other stuff is left as an exercise. If you have less than 4 hard legs, so I and j run from 1 to n, if n is equal or smaller than 3.
Simone, there's a question on the chat.
Sure, so should maybe n? Yeah, you're right. Thank you. Thanks, Steve. I'll double check in my notes, but I think you're perfectly right. If n is less than 3, then one can show that you can always diagonalize these color operators. So these color operators can be written as a combination of cousins of CF and CA. If instead n is bigger than 3, then you really have to deal with complicated color matrices. So color is complicated. Well, the soft emissions in QCD are difficult because they know about the color structure of the event, and that's why they're also difficult to implement in general purpose event generators. So the forefront of development of these event generators, like I'm sure you've heard of Pythia, Herwig, and Sherpa. Now there's an effort to improve these generators so they can fully account for color effects. And one of the difficult parts that people need to address is that really, if you want to take into account soft gluon emission, which are not necessarily in the coordinate limit, then you have to deal with this color amplitudes. Okay, so this one difficulty of soft emission. The other difficulty with respect to QED. So if you were doing QED, then essentially that would be it. So you have a full factorization at the level of one emission, but then you can show that n emission are just a copy of one emission. And essentially, because in QED, the only thing that can happen is that you have a cascade of soft gluon emission. QCD is more complicated, of course, because even if you start with a quark and say you need a gluon, then this gluon can split into gluons, while a photon cannot split into two photons. And so proving that indeed you have a full factorization in QCD, it's actually quite hard. Although it can be, factorization does hold with certain assumptions. So to cut a very long story short, in QED, it's not a difficult exercise to show the soft gluon emission factorized, and more than that, the exponential. So if you sum over all possible emission, an infinite number of soft emission QED, you get an exponential. This is done. There's a beautiful chapter in Steven Weinberg's book that does that. In QCD, that's much more complicated, but indeed you can achieve a exponentiation also in QCD. Of course, it's a more complicated form of exponentiation because it involves exponentials, because the matrix, you don't exponentiate an amplitude, but the amplitude itself, it's a matrix in color space. And also you have to account for these non-abelian splittings. But you can arrive at a similar result, which is known as non-abelian exponentiation. And so soft gluons can be resummed in QCD as well. Now, because they're complicated, from now on, I'm going to concentrate on the collinear limit because it's easier to deal with. Nevertheless, I think one should stress that because soft gluons are more complicated, that's where the fun is. So if things can go wrong in performing resummation or cancelling Fourier divergency, they'll probably go wrong in the soft sector because it's more complicated. So, for instance, there are tons of effects which are still under active. They constitute still an active area of research, and they all have to do with soft physics in QCD. For instance, if factorization, this picture of separating perturbative and non-perturbative degrees of freedom breaks, it probably does so in relation with soft emission. There are non-trivial effects that are called, they go under the name of coherence violation. So there's something that spoils this non-abelian exponentiation as such. And something that we'll mention towards the end of the lecture course is there are complicated, there are structures, all of the structures which are difficult to achieve in QCD. They are due to things which are called non-global logs. So really, what I wanted to say is that it's a difficult problem, and because it's a difficult problem, it's still actively researched. And if you want to try to do something new in this field, that's probably where you want to look. Okay, so as I said, that was a very brief and summary. Let me see if I said everything I wanted to say of soft effects in QCD. And it's very quick, so I'm happy to take questions in the discussion session. Okay, so what I wanted to discuss instead with you today is how phenomenologically we study an actual observer. And so let's go back to our process, which is Dralian, and let me treat it in the usual number with approximation, so it's easy. So I have my two partons coming in, and I have my Z boson, plus mu minus, and then I have QCD radiation, which I collectively call X. So let's go step by step. So I would like to build an observable which would allow me to probe QCD radiation in this process. And I want the observable to have three features. First of all, I would like, from an experimental viewpoint, to make the observable simple and clean. Clean meaning easy to measure. So if you remember, when we did deep inelastic scattering experiments, where we mentioned deep inelastic scattering measurements, one feature which was very appealing of deep inelastic scattering is that you never ever measure the hadronic state that you produce. You only measure properties of the scattered electron. So we would like to do something similar. Can we find an observable that allows us to probe the dynamics of X without measuring X? So we want to measure an observable which only depends on the muon, or let's make even things simpler, something that depends on the Z kinematics. So to be precise, should be of the muon pair kinematics, but we work in another with approximation, so we can say the Z kinematics. Then, of course, these observables should be able to probe QCD dynamics. I mean, that's what we want to do. And C, I guess you should know now, but it should be RC safe, because I would like to compute something. Okay, let's have a look at the Z kinematics. So if we parameterize the kinematics of the Z, say we can do this in the lab frame or in the partonic central mass frame, or that's equivalent for what I'm going to say. Useful way of parameterizing the full momentum is by using variables which are very important for hadron collider kinematics. So I can write these as transverse mass times hyperbolic sine, cosine of the rapidity. I'm going to discuss this in a moment. Qtx, Qty, mt, hyperbolic sine of the rapidity. So what is the transverse mass? The transverse mass square is the mass of the Z boson plus its transfer momentum square, and Qt square is Qtx plus Qty. And you can show, that's easy to do, so I leave it to you, Q square. So this is the parameterization of an on-shell Z boson, which we can use because we're doing the Norwood approximation. Otherwise, instead of nz, put Q square. So I'm introduced two variables which are very useful for the hadron collider. One is the rapidity of the Z boson with respect to, maybe I should say that when we do hadron collider, I always assume the Z axis is the beam axis, and then perpendicularly to the beam axis, there's the transverse plane. So X and Y leaving the transverse plane, and Z is along the beam axis. So the rapidity with respect to the beam, it's the Lorentz rapidity. So it depends on the longitudinal degrees of freedom, and the other guy which I introduced is the transfer momentum. Okay, so I could choose, both are interesting, and actually both are measured at the LHC. So the rapidity distribution of the Z boson is an interesting way of probing the dynamics, and also the transfer momentum. It's very interesting. We can do actually both at the same time. Now, the rapidity, actually, it's important if you want to learn about PDFs, because the rapidity tells us something about the boost along the Z-axis of the Z boson. And this has to do with the, how big are the Z1 and Z2 fraction that you pick up from the protons. If instead you want to probe final state radiation, then Qt is probably a better choice. Why is that? Well, if you imagine to work at alpha s to the 0, so the linear order approximation that we discussed now a couple of days ago, well, at order alpha s to the 0, the Z is produced without any other particle. And so at alpha s to the 0, Qt must be 0, because your two partons are colliding, and they're moving parallel with the same direction as the protons, so along the Z-axis, they collide, and so there's no transfer momentum before the collision, so there must be no transfer momentum at the end of the collision, but the only particle in the final state is the Z, so its transfer momentum must be 0. So any sign of Qt being different than 0, then it's a probe, it's a direct probe of the recoil system, the system that is recoiling against the Z boson. You always have momentum conservation, and in collinear factorization, the initial state transfer momentum is always 0, because the partons in collinear factorization are always moving along the beam. And so the total transfer momentum of the final system should be 0. And so if you have other emission, I guess you can write it like that. So the transfer momentum of the Z boson must be opposite to the total transfer momentum of this hadronic state X we want to set. So indeed, Qt is a direct measurement of QCD radiation. On the other hand, Qt only depends on the Z kinematics, because in order to measure Qt, you only have to, find your muons, reconstruct the momentum, the full momentum of the Z boson, and derive what is its transfer momentum. So A and B are satisfied. Is Qt IRC safe? Well, yes, it is, because the Qt of the by using this this relation here. Oops, sorry about that. Oh. The Qt we want to measure must be minus the sum of all the transmomenta of the particles I'm producing. So it's linear in the momentum. So if two particles go collinear, then the transmomentum always with respect to the b. That the transmomentum is the sum of the two. And if one particle goes soft, then its transmomentum goes to 0. So it doesn't depend, it doesn't contribute to the observer. So indeed, Qt is an ISC safe observer, which means we can calculate it in perturbative physics. Okay, and we are very happy and to do so. So, okay, I think I screwed up some signs. I'll try and check. Okay, so we need to try and evaluate the Qt distribution at order alpha s. We already seen there are two types of contribution to this order. So we have a contribution A, where you have quark, anti-quark in the initial state. And you have your Z boson, gluon, plus the cross diagonal. Sorry, cross. I mean P1 and P2 has changed. And I don't write cross because then it might be confusing with other things that are called cross. And then there's another platonic channel where you have the quark and the gluon in the initial state. And here you have other diagrams, right? You can also have this guy. You also have another contribution, C, which are the virtual corrections. But the virtual correction, well, they contribute as a delta function in Qt, because there's no real recoil against the Z, so the virtual correction will leave at Qt equals 0. Let me write it in a different color. So if you want, we can say that the measurement function for 0 emission is a delta 2 of Qt. What is a measurement function for 1 emission instead? Well, we know that the transmomentum of the transmomentum of Qt plus the transmomentum Kt should sum to 0. And indeed, you can check that if you send Kt to 0, indeed, the measurement function O1 reduces to the measurement function O2. So what do we have to do? Well, what we have to do is that we have to take our matrix elements square and integrate them against this measurement function. Remember, what was our definition of a differential distribution? So you'll have to take A squared integrated against Qt plus Kt, and also okay, let me concentrate on this guy first, and then I'll comment on this. Okay, so how do I estimate these this contribution, let's say in the collinear limits. Actually, let's make things even simpler. Let's look at the soft and collinear limit. Okay, sometimes, I mean, I can do two things. I can look at the double differential distribution in the vector Qt, or I can look at the distribution as a function of the magnitude of Qt. Let's do the second one. I mean, with one emission, it doesn't really change very much at this order. It's a bit more, it's a bit subtle if you go with more emission. That's not what I want. Okay, so d sigma hat for subprocess A, differential in dQt square. Now we do this in the collinear limit. So remember, in the collinear limit, I have a factorization at the level of the matrix element square, and the matrix element square factorizes into the bone level times the splitting function integrated over the appropriate transform. So I can write this as alpha s. I write CF because that's the appropriate color factor, sigma 0, and then I have an integral d theta square over theta square. I have an integral in d phi. This integral in d phi is trivial, but it's trivial at this order, but let me write it for future reference. And then here I will have to write p q q z delta, and I'm differentiating the magnitude, so here I can write qt square minus kt square. Okay, now I said, sorry, it's an intro in this set. Now I want to work in the soft and collinear limit, and I'm parameterizing the momenta as follows. So I have an emission, and this carries the gluon. This is an initial state emission, so I'm following this convention. This is 1 minus z, this is z, and the angle between the two is theta. And I want to work in the limit where the gluon is soft, so where z goes to 1. And so instead of pqq, I'm just going to write the most singular term as z goes to 1, which is 1 z. Okay, at this order, so the integral in phi is trivial. So I'll do it. Instead of writing down, instead of doing the integral, let me do a change of variable. So I'm going to call, I want to integrate in kt. Let me do this change of variable. Sorry, I'm going to introduce a delta, which is defined as 1 minus z times theta. Why, if I do that, then this integral is alpha s cf by 2. I change, instead of theta, I write this integral, so this d delta over delta. Then I have this 1 minus z t square. And okay, so what is this delta? Well, delta is some sort, it's essentially a dimensionless transfer momentum. So the transfer momentum of this gluon with respect to the emitting quark is given by its kt is given by delta times the sort of like the hard scale of the process, the only hard scale that we have, which is okay. So here I have minus delta square q square. Okay, I'm almost done. The only thing I need to, well, now what I want to do is to do the integral. The only thing I need to remember is that the only thing I need to pay attention are the fact that by this change of variable, I'm actually mixing the integration region, and so the upper limit on the z integration will actually depend on delta itself. So if you do if you go through the kinematics, you'll find that the upper limit of this integration is of the order of 1 minus delta. Okay. Now it's not difficult to do the integral. I can use directly the delta function to integrate over delta, and if I do so, what I get is alpha s cf over pi sigma 0, and then what do I have? Well, if I can write down no, okay, sorry, let me write it like that. This was theta squared, so the change of variable naturally with Jacobian 1 gave delta square, and then I have the integral dz 1 minus z between 0 and 1 minus qt over q. One over q squared. Okay, if I do this integral, you see now I have a logarithmic integral, and this logarithmic integral would be divergent when z goes to 1, but the singularity is cured by the fact that I have a fixed value of qt. And so the resulting integral is finite, and that's this structure. Minus alpha s over 2 pi, 1 over qt squared, log of qt squared divided by q squared, plus contribution, which are less singular than 1 over qt log of qt over q when qt is small. So we find a finite answer, which is what we expect because the observable is infrared and collinear safe. But you see that we find a very interesting structure. So remember, we're working in the collinear limit, and in the collinear limit, we expect qt to be small. And in this limit, we find that we find a term which contains a 1 over qt singularity, but 1 over qt term times the log. So this is often referred to as a double logarithmic behavior. It might be a bit confusing because it's only one log, but usually one counts this 1 over qt also as a log, because if you were to integrate, you'll get a log as one. And so we see something interesting, but a little bit problematic. So if I compute the distribution at order alpha s, I find an answer which is finite. But if I push qt to be smaller and smaller, this answer becomes, this contribution becomes bigger and bigger. And to the point where alpha s times this contribution may be a contribution of order 1. Okay, so so we should question ourselves, okay, I'm happy with this answer. I'm a bit worried about this answer if I want to probe the region where qt is small with respect of the hard scale of the process q. Okay, so there's no hope that this behavior will cancel against other anything else, because we've seen that the visual contribution live at delta equals 0. Okay, so they don't have any finite qt dependence. And what about the sigma b contribution? So the b contribution, well, it's a different subprocess, so it won't cancel this behavior. And actually, if you do the calculation, you find that it's a bit less singular. So the contribution, if you do the calculation for the subprocess b, you'll find that it only has a single log. So this order is only ever 1 of qt contribution. Now I'm going to state something without proving, is that this pattern actually persists at higher orders. So if you were brave enough to compute, you can do this in the collinear limit. These observable at order alpha is squared, alpha is cubed, and so on and so forth, you will find the following structure. So let me write it in n space because it's a bit easier. Square 1 over sigma 0. So if I'm in n space, this depends on n, qt, the hard scale of the process, and alpha s. And we find this distribution as qt squared goes to 0 as the following behavior. There's a 1 over qt squared overall. Then there's a sum and 1 to infinity of alpha s 2 pi to the n. Remember, I'm doing n orders of perturbation theory. Some coefficient an log n minus 1 qt squared. Then I have again 1 over qt squared, and then I have a sum and 1 to infinity alpha s 2 pi to the n bn, and this coefficient can depend on the Mellin variable, right? Log 2, sorry, 2 to n minus 1 to n minus 2 qt squared over q squared, and so on. So at every order in perturbation theory, you find contribution which have the form alpha strong times some power, alpha log alpha strong to some power times the power of the log. And the one contribution I've written in red, they're usually called double logs or leading logs because they have the maximum power of the log which is possible. And then the terms in blue are called next leading log, and so on and so forth. And then you also have terms which are regular as qt equals to 0. Okay. So if you, this is a bad situation to be in, because if you're interested in the region where qt is much smaller than q, then every time you add a power of alpha strong, you're adding contribution which is potentially of order 1, because even if alpha s is small, alpha s to the n log 2n minus 1 of qt squared over q could be of order 1. Okay, you're multiplying a small number times a number which is potentially very big, and so you can get something of order 1. And these, you see these if you plot your distribution. So if you really plotted the Havenberg, the sigma, the qt, you'll find, okay, say, okay, I do the leading order alpha s calculation, and I find something like that. It goes like 1 over qt times the log. And then I do the order alpha s squared calculation, and I find something that a large qt seems okay, and then it goes like that. Now we know that the integral of these curves is finite, because there's a delta function which lives at qt equals 0, which will make the integral finite. But you see that experimentally, I would like to say, okay, but do I trust my answer here? And you don't know what to do, because every time you add, you don't know what to believe, because every time you add an order perturbation theory, you get a completely different behavior. And so what we'd like to do in the remaining time is to find a way of accounting for this large contribution. So this contribution that makes the perturbative expansion unstable at this precise logarithmic contribution. And so we would like to find a way to account for this problematic contribution to all orders in perturbation theory. Another way, we would like to rearrange the perturbative expansion so that is not in the regional small qt is not expansion in powers of alpha s at fixed alpha s, but it's an expansion in powers of alpha s where all the terms which are alpha s times the log are counted as order 1 term. And this procedure is called resummation. So you are resumming the perturbative expansion in a limited region of vector space. So for Qt, this is actually not too difficult to achieve, at least at the first non-trivial order. And there's a beautiful paper, 1979 paper by Parisi and Petronzio. That's the second time we mentioned Parisi, still not for the Nobel Prize. And I'm going to just, what I want to do in the before the break is I would like to sketch the derivation of this resum expansion. Okay, and we'll do so in the Euclidean limit, but actually this is enough to capture all the essential physics. Okay, so what we would like to do in principle, but we would like to account for any number of emission, say of, let's start with collinear gluons. Okay, how do we do that? Well, okay, so we want to compute 1 over sigma 0, d sigma hat, EQT. I'm doing this for the double differential. Okay, so this is a function of n qt q square and plus. Okay, so if I work in the collinear limit, I can write down a factorized expression. What does it look like? Well, I have to consider the emission of n gluons. So I have n times the phase space for the emission of one gluon. So I have EKT I square over KTI square d phi 2 pi d zi. I goes from 1 to n. These are identical gluons, so I put 1 over factor. For each emission, I have 1 power of alpha s. And someone told me that this emission should be evaluated at the relevant transform moment. We're going to say that we're not going to show it. Actually, this alpha s should be computed in a scheme which is not precisely ms bar if you want to achieve full next to the log summation, but that's a detail that I'll write it, but it's not going to be crucial for us. And then for each emission, I have my splitting function. Now, all this emission will be, the integral over z is rather complicated because we need to account, it will give us to a convolutional structure. And so we, as I've written here, we'll consider Melling moments of this guy. Okay, and then I have a theta function which ensures energy conservation. Well, it's the same. Sorry, is the equivalent of this bound here. Okay. Okay, so far matrix element. Now I have to write down the observable, and I'm going to write down both real and virtual contribution. So I have the real contribution. It tells me that my Qt is given, is given by the sum I1 to n of Kti. And the virtual correction leaves a 0. And the virtual correction also leaves a z1. So this is the matrix element for the emission of n gluons collinear to the incoming pole. And now I have to sum over all possibilities. I want 1 gluon, 2 gluons, 3 gluons, 4 gluons, 2 gluons, or 0 gluon. That's the linear. Okay, we just written down our first resum formula, so we'll start. What do we notice? Well, everything looks factorized because we work in the collinear limit, apart from one thing. there's one thing, and moreover, everything looks factorized, and you see that essentially it hints to an exponential, because we are summing 1 over n factorial times, something that looks like x to the n. Apart from one contribution, which is annoying, which is this contribution here. This contribution is not factorized. You see they contain, the delta function, the observables contains the sum over n. And this is usually the case. So if you have IRC set observables, very often you have this situation. Everything is factorized apart from the observable. But this is crucial. And this was the contribution of Parisian Petronius, because this delta function tells you that you can have 0 transfer momentum of the Z boson when the KT, the different KT conjecture, they sum up to 0, even if they're not individually solved. Okay, so it's very important that there's a 2-dimensional delta function. How do you go about that? Well, standard trick in this business is to try to find a different representation, to try to go in a conjugate space. In the same way as we had convolution over Z, we went to a conjugate space, which was Manning space. And here we want to do a similar thing. So we have a delta function, and we want to go in a conjugate space where this delta function is factorized. And it's a 2-dimensional delta function, and so the right thing to do is to use a Fourier Transform. So the standard trick is to remember that KTI, this 2-dimensional delta function can be written as, there's a constant, and then you go to conjugate P space, e to the I, P, Q, and then you have a product I to N, e to the I, K, Ti dot B. Okay, so if you use this representation, then you can do, then you can achieve a factorized form. And you get, what is the price you pay is that then at the end of your calculation, you have to go back from Fourier space to physical space. So if you do so, what you get is 1 over 4 pi. There will be this integral over B that you leave at the very end. You see it is an inverse Fourier transform that you have to do in the end. But then if you do so, then you see that everything is factorized. You also do, delta 2 of Q is easy to treat in this way as well. And you find that you can sum this series to an exponential. And what does the exponential look like? Well, I will have an integral dkt squared. Dkt squared is alpha s cmw of kt squared over 2 pi. Then you have dz d phi 2 pi. See, now I don't have any index I anymore because I've summed the series. P, Q, Q, Z. And then I have Z n minus 1. Okay. E to the I B dot kt minus 1. These are the Virchow corrections. Theta 1 minus Z minus kt squared. And this is sometimes written as so whatever is in the exponent is usually called pi square e to the minus r of p. You can show it's only a function of the absolute value of p. And this function, well, its various name is sometimes called the radiator or the pseudo-Gromf factor. or the resummed exponent, the name all you want. What it does, it resums large logs. So through this Fourier transform, we turn the problem of resumming logs of Qt into resumming logs of B. You can do this exercise to show that one of the Qt log of Qt, if you take the Fourier transform, it maps into a log of B. It's an exercise. And what is the form of this radiator? So you can do these integrals. I mean, it's not trivial, but all these integrals can be done. And to the accuracy that we are interested in, which is called, I'll define a bit later what I mean, next with log accuracy, the radiator is actually as a rather simple form. So it has it's an integral between Qt and B bar power minus 2 bkt square over kt square alpha s of kt square. So you still have to do the integral of Brownian coupling. And then there's this structure, coefficient A1 plus A2 alpha s of kt square over pi log q square kt. So this term A2 comes from this CMW scheme that I mentioned earlier. That is another contribution, which is usually called B1. Sorry, wrong place for the bracket here. And then if you do the Z integral, you see that you take the Mellin transform of the splitting function, and so you get the anomalous direction. And B bar is just B times some constant. It's B to the Euler gamma. So this order, the result exponent has a rather simple form. You can do the integrals of the Brownian coupling. This A coefficient, they have a famous name. They're called the Caspar anomalous dimension. So A1 is CF for us. If we were to do gluon scattering, it would be CA, and it's a one loop Caspar anomalous dimension. And A2 is the two loop Caspar anomalous dimension. B1 is related to the endpoint of the splitting function, and we said the gamma QQ is the delta Rayleigh Parisi anomalous dimension. And you see that the gamma QQ as you can do an interesting thing. Imagine that you mount this guy. So these guys multiply the PDFs. And so gamma QQ in the exponent integrated between Q square and 1 over B square, what it does is that it moves it evolves the PDFs from the hard scale Q square to the scale 1 over B square. So you have this interesting interpretation. So that the relevant scale, when you do Qt resummation, the relevant scale of the PDFs is not the hard scale, but is this 1 over B square scale. Okay, if you do these integrals, and I invite you to do, you will discover the usual problem with the Landau pole, but you'll find out that you can write RB in this form. There will be L, G, here it depends on the notation that you follow. Let's call it G0. No, let's call it G1. It's more. And L, these are the logs we are summing, are logs of B bar square times Q square. So logs of Qt are mapped in logs of B. And you see now that we achieve what we were after. Now RB as a form which is an expansion in alpha S, but alpha S log is kept fixed. And here, if you were brave enough to compute G3, you'll have alpha as G3, alpha as log. So alpha s times a log is an order one quantity, so I keep it free, I keep it fixed, and then I expand in power of alpha s. And if I do a calculation where I keep only this contribution GR, G1, then I do what is known as the leading log calculation. If I compute G2, then I do a next to leading log calculation. And if I compute G3, then I do a next to leading log calculation, and so on and so forth. And so you see that this is a different way of looking at the perturbative expansion. Notice that it's built upon the collinear approximation, and so it's not valid everywhere. It's only valid where the collinear approximation is appropriate, meaning a low value of Qt. So now I'll ask you, I have really a couple of things still to say about this topic, maybe like 5 minutes. Do you want me to go on a little bit into the second hour and then break after, or do you want to take a break now? I am happy both ways.
No, Simone, how you prefer. So
okay. And I'll still do another 5 minutes so we close this topic, and then we'll start fresh with something. So we're going to do the break. Don't worry. Okay, so let me write down the final formula that one achieved when we put together the Platonic calculation with the Hadronic one. So what we get, actually, let me do it like that. Because there's no point in me writing this 5 times. So I'm just going to steal. That's fine with me. Okay, so I know it's cheating, but okay, so if we mount everything together, so we put the PDFs and to get the hadron level cross section. So what we're going to have the 2 PDFs, FA and FB, and remember I can use their contribution in the radiator to evaluate the PDF rather than scale Q square at the scale 1/b square. So we understand the origin of this. And then we have to, we have the Platonic cross-section result, which here I call W, AB, and then we have to do the convolution against the PDF. Now here, I guess maybe one surprising thing is that you see a Bessel function appeared. Don't be worried. The only reason that this Bessel function appears is because here I'm looking at d sigma Qt square. So I'm integrating the all possible directions of Qt, which means that I have to integrate. This function here. And if you do this integral over the angle between Qt and B, you get a Bessel function. So nothing to worry about. Okay, so more interesting for us, what is the structure of this W? Well, W contains a sum. Well, if you write, here, if we write it in direct space, it contains convolutions. And then you have some function, C, CA. I'll write it and then I'll comment. C, B, Z2, alpha s 1/b bar. So this is the product of 2 functions, which are function of alpha s evaluated again on the scale 1/b. Then I have the Born cross-section, which for us is a CC bar or QQ bar to Z. I'm summing over all possible by Z. Then I have some virtual corrections, which don't enter at the order we calculated, but they will be there at high order. And then I have my resum exponent. over the super. So let's look at a picture. So I have my incoming protons. Now the PDFs here, these PDFs are evaluated at the scale 1/v bar. Then I have this function C. These functions C are called collinear functions. So they describe emissions which are collinear to the initial, the incoming length. Then I have a hard function. The hard function then will provide me. And on top of that, I have the pseudocode, which describes soft radiation. So this is the sort of, one thing about resummation is imagining to divide up the cross-section into different regions of integration. And this region is described to all orders in integration theory by a function, collinear function or hard function or the pseudo. This way of separating or refactorizing the cross-section is essentially the starting point of soft collinear effective theory. So resummation done in the language of collinear effective theory precisely aims to separate modes that contribute to our observable so that the cross-section can be appropriately factorized. It's not necessary to do soft collinear effective theory for resummation, but it's a nice way of organizing the calculation. Two things to be careful. First of all, the inverse, the last integral that you have to do, so this integral over B is not well defined because of the Landau pole, so you need the prescription to do it. And the other thing that one may be tempted to do is to generalize these to processes which have gluons in the initial state, but the generalization is not true. Okay, so what do we achieve? We achieve the resummation. Okay, and we understood that the resummation can be done at different accuracy. Leading log, next to leading log, next to next to. This resummation is accurate when Qt, transfer momentum, is much smaller than Q squared, the hard scale of the process. Of course, Qt should be also much bigger than lambda QCD, otherwise perturbation theory is rubbish. On the other hand, we don't expect this calculation, the result calculation, to be accurate in the region where Qt is of the order of Q squared. On the other hand, we can do a fixed order calculation. Leading order, next leading order, next leading order, and so forth. And so the fixed order calculation should be good when Qt, when there's no hierarchy of scale, so when Qt and Q are of the same order, but fails, and as we've seen, where Qt is much smaller than Q squared. So if I go back to my picture here, okay, so if you remember, we've seen that the fixed order calculation completely fails in this region. On the other hand, there is some calculation would fail in the region of large Qt. So the best of the worst comes if you combine them. So you can define what you usually refer to as a d sigma dQt matched when you take the fixed order calculation. And the best we can do now for this observable now is next to next to the order. You add the resum calculation, and the best thing we can do here is n cubed. And then, of course, you have to subtract the double count. Okay, because both calculation accounts for some contributions. And if you do so and you plot it, then you find something that looks like that. In the region of large Qt, it will follow the fixed order calculation. But then it will depart and will describe a sensible spectrum. And if you look at the data, indeed the data, which now I'm drawing in a very precise way, are well described by this resum and match approach. Why do we trust this this calculation? Well, there will be a fixed order region. There will be a resound region. And if you do, so if you only do fixed order, you trust your calculation only up to here. Then you do resummation, so you can also trust the calculation down to here. Okay, there's still a region which we struggle to describe. And this will be this region here. And in this region, no perturbative effects will be large. And so you'll have to do some modeling to describe also the very low region. So in other words, the assumption that Qt is much larger than the QCD, if you go to very, very small Qt, no longer holds. And so you need to do some more. Okay, so it was a bit of a marathon, but this is a complete resound calculation. And it was one of the simplest one I could think of that fitted our course. So I'm gonna leave you with a sentence which I really like by one of the masters in this business, which is George Sterman, which at the summer school a few years ago says this: resummation just scratches the surface of QCD, but it makes some mark. It's a way that the resummation is useful to describe data, but also it opens up a window into all order field theory, which is also quite interesting. And if you suffer from it, you can turn this sentence and say that it leaves a scar, but that's a different point. Okay, I should stop here. Maybe it's good time for a break, and we resume in 10 minutes. Okay, so we now change topic, and we start lecture 4 with a bit of delay, but this will be really more like a chat rather than actually doing calculation. So again, we go back to our problem or our question that we would like to study QCD radiation. So we take the same process, Z recalling against some hadronic activity, and we ask the following question. Fine, we developed a calculation scheme to compute a clean observable, so the PT of the Z boson. And with this, we can understand something about the system that the Z boson is recoiling against. However, well, now we start to be a bit more picky about our things. We would like to understand things in more detail. So can we study something more about X, about the hadronic system X? X will be a collection of hadrons that fragment into, well, collection of partons from the point of view of perturbative QCD that fragment into hadrons that are collected into the calorimeter. Can we give a perturbative description of X? And does this perturbative description have anything to do with nature? Or in other words, can we compute some observable on X so that if we compute it, if you evaluate our observable over the partonic system, these resemble what will be measured by the experimentalist on hadrons? Well, we can try and ask this question and see, okay, let's start at order alpha s. We've done this, we've drawn these diagrams many times. What we can say about our system X at order alpha s. Now I start at order alpha s because alpha s is 0, there's nothing, right? So I've drawn these 100 times now, but we have these two types of diagram. So at order alpha s, the recoiling system X is either a gluon or a quark. The kinematic distribution of this recoiling system, so these gluons, are strictly related to the one of the Z boson. Actually, at this order, almost in a trivial way, because you need to conserve energy and momentum. And so really, there's nothing much more that you can learn about the distribution of X than you didn't know from the distribution of Z. Things become a little bit more interesting if you go to order alpha squared. Because now, for instance, the kinematic distribution of the system are still related with the to the one of the Z, but you have more patterns, so you can have more configurations. So what you can have at order alpha s? Well, at order alpha s, we can have two partons, or one, so let's say two real emission, or one real and one loop. So for instance, you can have something like that. Or you can have something like that. So we can ask ourselves, okay, well, what will happen? Well, if we compute, real and virtual, we expect the initial state radiation will lead some collinear singularity that we need to resolve in a PDS at order alpha s square. However, for all the other singularities, soft singularities should cancel in some real and virtual. Now, let me ask a specific question. Can I compute the cross-section for Z plus 2 gluons? So I know it's a stupid question because we cannot measure gluons, but remember the spirit. So if we can find an observable which makes sense at parton level, we can hope that also bears some similarities with the corresponding observables at atom level. If the observable doesn't even make sense at parton level, then game over. So let's compute the let's try and compute its observable. Well, now we have a problem, because let's imagine we want to separate the category of like Z plus 1 parton and Z plus 2 partons. Now, if we do Z plus 1 and only 1 parton, well, let me turn it in another way. So if I do Z plus 2 partons, and I look at the limit where the two partons become soft or collinear, then I'm in trouble, because I would like to cancel these singularities against the virtual corrections. But the virtual corrections only contain one partons, real parton in the final state. And if I'm separating the two categories, 1 partons and 2 partons, then I cannot sum real and virtual together. And my cross-sections would be my partonic cross-section would be divergent. In other words, this is yet another example of something we said a couple of hours ago or before. Multiplicity is never something that it's almost never something that we can compute, because the number of partons strongly depends on partonic splitting. And you see these at work. I mean, if you insist on 2 partons, but one of the two becomes soft, and you don't have the corresponding virtual correction to cancel the singularity, then you do it. So what we like to do is that we need to still be a little bit more inclusive. Of course, we don't have to be fully inclusive, otherwise we're back at what we were doing before. So we want to try and separate 2 categories, 1 and 2 something, but a little bit more inclusive, the same 1 and 2 partons. So for instance, what we would like to say is that, okay, let's assume I have my configuration where I have my Z boson, and against the Z boson, I have 2 partons that recoil. If these 2 partons are very close in angle, but one of them is soft, then I would like to define an object which puts them together. This way, I can put them together with the virtual correction, which I don't know how to write in this. Let's put it like that. On the other hand, if the 2 emissions are well separated, so I have my Z that records against 2 well separated emissions, then I can afford to call these 2 emissions 2 objects. So I would like to define something that tells me, look, if your 2 partons are far away and hard, assign each of them into a different object. if the two partons are close to each other and you enter a region, a danger region, because you can have collinear singularity, or one of the two guys is soft, so it could be very far away, but soft, and so cannot be resolved, then put them together in one object and add to this object the virtual corrections. So you can cancel the singularity. And that's the game we're going to play. These objects are called jets. So jets are the closest thing to the concept of parton that we can use, which is safe to compute in perturbative QCD. Okay, so I have to still have some inclusivity. So if two things are set, cannot be resolved, I need to put them together. But I'm not going to be fully inclusive, because if I can separate, say, two partons from the point of view of perturbative QCD, I can put them into different jets. So what do I call jets? So they're called jets, well, because indeed, if you do high energy collisions, what we observe experimentally is that the QCD radiation, which gives rise to hadrons, is not uniformly distributed, but rather it appears as streams, beams, or sprays, if you want, of fairly correlated objects. So that's an experimental evidence. We do proton-proton collision. This is an event display from Atlas, and you see that you don't have a uniform cloud of radiation, but radiation, these hits are in the hadronic colorimeter, looks like concentrating into different directions. So there's experimental evidence, the fact that these objects that these categories that we'll try to build actually have some physical barrier. And indeed, we can actually, we don't have to define, you can define them essentially in sorry, I shouldn't swear on the these objects actually have some geometrical interpretation and physical interpretation as well. So do we understand why they form in this way? Actually, jet formation is a rather complex topic, but the first approximation is not difficult to understand why we have jets. Remember that QCD splittings are announced in the collinear limit. So every time we have a splitting perturbatively, we have a power of alpha s. We have this measure and the splitting function. And so it's more likely that QCD emission all happen at rather small angle because of this enhancement factor. And eventually this guy will, by splitting, they will sort of lose a little bit of the energy, and they will eventually hadronize in things that we measure in lambda, okay, in the colorimeter. And so indeed, what the colorimeter will see is that these hadrons, or the decay products of the hadrons, will hit cells which are nearby, geometrically nearby. And so they lit up a region of the colorimeter, which is rather contained in terms of spatial dimension. So QCD radiation is collimated along hard directions, and this is essentially, this brings naturally the concept of jet. And the parton to hadron transition doesn't spoil this picture. It could have been very different. I mean, QCD could be like a strongly coupled theory with like a symmetric, spherical symmetric type of decays. In that case, we want jet. But if you want, jet formation is an experimental evidence of perturbative QCD, because jets are a prediction of perturbative QCD. So jets are my bread and butter. That's what I do in my research. And what I will try to do for the remaining part of this lecture and tomorrow's lecture is try to give you First, a sense of the basic concept, and that's why the second part of our lecture today will be more of a discussion. And then tomorrow I'll try to dig into a more frontier question, and I will talk about gesture structure and how we try and understand the internal structure of jets and why this is interesting. One thing I really like about jets is that they really live at the boundary between theory and experiment. And so for someone who's interested in phenomenology, this is really like the best. It gives like the opportunity to talk to both worlds. And indeed, if you ever go to a conference on jets, well, in a world where we can go to conferences, you'll find theorists and experimentalists alike. I mean, if you go to a conference on next order calculation, most of the audience will be theorists. If you go to a conference about jets, you'll see 50-50. And many times you actually see papers written together by theorists and experimentalists. So from the point of view of the theorists, the jets are the way we can turn a calculation done with partons, and bear in mind, we're not very clever, so we can do calculation for a limited number of partons, into something which is actually experimentally measured. It would be way more difficult, and we could do the less precise way if we were to try and compute the cross section for, and this is picture, the production of a pi 0, a pi plus, a lambda, and a k. That would be a very difficult calculation to do, and there will be a lot of non-perturbative information that we need to model. On the other hand, if we, happy to accept some inclusivity and we say, well, I'll compute the transmomental distribution of the jet, that's actually something that you can do in an easier way. You can work with your partons, and the correction that brings you to parton level to hadron level are genuine power corrections. Okay, so there are contributions that go like lambda QCD over Q. So that's from the theory viewpoint. From an experimental viewpoint, well, jets must be something usable in experiments. And when I mean usable experiments, I mean that you should be able to define jets using either particles or even a lower level using calorimetric information. So really, the concept of jets that we will try to make more precise in what follows should really be usable for both theorists and experimentalists alike. And of course, as a theorist, we further require one thing, that we would like to be able to do calculation with this jet. And so we would like to have infrared and Qtisc Safe. So. Now, let's see if I can bring this up. Do you see my screen with the slides?
Yes, we can see your slides.
Okay. And you see them changing?
Yes, they are changing.
Okay, so since this is really like a more relaxed conversation, okay, this will work much better in presence because I have questions and now I cannot read the answer. I take a jet from the ancient time. This is an event display from lab. I was in high school, so I guess you were not even born. And so this is the view of the transverse plane. So the beams are going into the center perpendicular to the screens. And you see these are the sort of, you see this blue line, which are the tracks. So there's a high magnetic field that bends your particle, and these particles they leave the charged particle, they leave some traces, and this is what you see in blue, and then you hit the electromagnetic calorimeter and then the hadronic calorimeter at the other side. So you see this picture, and I think any of us would say, well, here there are two jets. Okay, it can't be more clear. And so we attempted to draw some cones around this this radiation. But sometimes, many times actually, eyeballing is not enough. So if I were to show another display, that looks a little bit more messy. Okay, and here the questions like how many jets do we see becomes more of an ambiguous question. Okay, because I could say, well, I see 3 jets, so this is a 3-jet event. Maybe I see 4. Okay, so I really need a way of defining jets. So I'm switching back and forward. Okay, so what I really need is a jet definition. And what goes into this jet definition? Well, first of all, I need, so you see these cells or these patterns, I need to decide whether 2 objects are, so I want to put together in one jet objects which are in some sense nearby, okay? So I need a way to decide which objects are close to each other, so I can put them into the same jet. And this is usually achieved through a jet algorithm. For instance, the anti-Kt jet, and so on. So this is a way that tells me, like, how do I decide? What is the, how do I decide? On top of that, I also need something that tells me parametrically, what does it mean being far away? Okay, so in other words, remember the example between 3 jets and 4 jets. What changes there is the resolution at which I look my event. Okay, so I need a set of parameters, a set of numbers that tell me how, whether I should look fine-grained or coarse-grained. So a jet definition contains an algorithm, but also contains some parameters. For instance, the jet radius. That's another thing which is sometimes overseen, but it's important, is that at the end of the day, I would like to tell you what is the momentum of the jet. And so someone needs to tell me how do I combine the momentum, how do I combine together the momentum of the particles to get the momentum of the jet. And this is called the recombination scheme. I mean, the most used one is the most obvious, which is just add the 4 momentum, but it's not the only one. Okay. So people argue a lot about jet definition, and one thing which should be very clear is that there's not an a priori jet definition which is better than another. So people should make a list of things they want the jet definition to be or to do for them, and then decide among different options. So there was a big meeting in the 90s that tried to sort of like put together the ideas that experimentalists and theorists had about jets, and what were the sort of like key points that jet definitions should respect. This is was known as the Snow-Mass Accord in the 90s, and it states things which were very, very simple. So from an experimental viewpoint, you want your jet definition to be able to be implemented. You want to be able to implement your jet definition in experimental analysis with thousands of particles. You want to be this jet definition to be as sensitive as possible to hadronization corrections, or even worse, remember we collide bunches of protons, so you have a lot of like a very noisy environment, so you want the jet definition to be robust against this type of effects. From the point of view of perturbative QCD, so what the theorists wanted, they say, look, I want this jet definition not to destroy my ability of computing this. So I want that a good jet definition should be such that if I compute a jet cross-section at any order in perturbation theory, I should get a finite answer. So these are very simple requirements, but actually, if you go back to the 1990s, early 2000, many of the jet algorithms that were used in the tevatron analysis were not infrared safe beyond next to Newton, which was fine at the time because the complexity of theory calculation was next to Newton at the time. But those algorithms are now useless because now we do next to Newton calculation, and some of those were just ill-defined at that point. Okay, so let me give you two examples of classes of jet definition. The first definition of a jet, I think, goes back to the 1970s, and it's a paper by George Sturman and Steve Weinberg, and they were looking at a plus and minus to two jets, and they gave the following definition of a jet of a two jet event. So you have your plus and minus coming in, they collide, and you have radiation. Okay, so you have radiation collimated along one line, and then you can also have some radiation around. And so they say the following thing: okay, I take E plus E minus, and I say that I get a two jet event if most of the energy that I measure in the final state is contained within two cones. So let's be precise. I want all of the energy, but a fraction epsilon to be contained in two cones of opening angle depth. So one can show sorry, my connection disappeared. One second. Can you still hear me?
We can see you, but no.
Not the slides. Yeah,
we don't see any sharing.
I think the Eduron. Let me try again. Probably there was a glitch in. Can you remake me host? Sorry, Julian. Yes, I'm sure.
I need to log in on the other.
Oh, okay, so sorry about that, guys.
Okay, now your iPad is can share.
Thank you. I apologize for this. So in this definition, which is one can show is infrared and Qtisc Safe, you can compute your cross-section. You see immediately two features. First of all, the cross-section depends on these two parameters, delta and epsilon. And this is an example of the fact that you need to assign parameters to define your jets. If you want this delta and epsilon represent the resolution at which you describe your jets. The other thing is that if you really, sometimes you often go into, you're interested in limit where epsilon is small and or delta is small if you're looking at narrow jets, and then not unexpectedly you will get in the your cross-section will contain terms which are logarithmic behavior upon your delta and your epsilon, or your resolution parameter. So more often than not, a good description of jet physics actually does include resonation. So that's another important thing to keep in mind. This type of definition of jets is called a cone jet definition of R. Now, nowadays, there actually are different types of arguments which are preferred, and I'll try and describe them in the very last part of this lecture. So, ideally, see in modern collider, most of the jet arguments that are used are called clustering. So they are arguments which build from a bottom-up approach. So the idea is that you start with your set of particles or pseudo-particles once you start combining things. And let's label two of them, I and J. Now, the algorithm computes mutual distances between all the particles. So it computes all the delta ij. Now, the distance will depend on a metric, which I'm not specifying at the moment, but it computes all of them. And it also computes some distance of each particle I from the beam. We're doing PP collision. Or this, if you're not doing PP collision, this could be an external parameter of your choice. Then the algorithm computes the minimum of all the mutual distances and all the DI. If the minimum is a mutual distance, then we recombine particle Y and particle I and particle J. For instance, we sum the full momentum. And now we obtain a pseudo-particle, because this is no longer a particle, it's just an object of my algorithm. If instead, if DIB is the minimum, then I called I, so this I here, a jet. And I remove it from the list. So in either case, I go from n particles or n pseudo-particles to n minus 1, because either I recombine two of them, or if one, or I remove because I identify a final state jet. And then 4, I go back to 1. But really, yeah, 1 or 2. So you see that if you iterate this argument, you know, at the end of the day, you start with a list of particles, and every time you run the argument, you reduce the number of particles, and you possibly add jets to your list, and at the end of the day, you're left with a list of jets. What are the properties of this jet? Well, every jet has a full momentum, which is defined by for instance, the combination of the full momentum of the particle. It has a jet axis, which can be defined either as the momentum of the jet with some other prescription. It has a list of constituents because the jet knows about the particles that were combined together. More interesting, and something that we'll exploit tomorrow, the jet has also, jets built this way have a clustering tree. So the jet remembers of like in which order the particles will merge together to form the jet. And all of these can be exploited to understand the internal dynamics of jets and hence QCD dynamics. Now, the very last thing I need to tell you before I we break for today is what do I choose for this distance? Well, in some sense, that's an arbitrary choice. A very popular choice nowadays is to use the so-called generalized Kt distances. So delta ij is defined in this way. It's the minimum of Kti to some power p, Ktj to some power p, and then a distance which is a geometrical distance. It's the distance in the azimuth rapidity plane. Divided by an external parameter which is called the jet radius. And according to the value of p that you pick, so these are p's, not meters, you can exploit different properties. So for instance, if you pick p equals 0, you lose all dependence on Kt, you have a purely geometrical algorithm. So particles are clustered together if they're closed in azimuth and rapidity, so if they're closed in angle. This is known as the Cambridge-Jacques algorithm. If you choose p equals 1, this is called the Durham or Kt algorithm. And what you do, say Kt, and this algorithm is the algorithm which is the most faithful to QCD. Because remember, what is the jet algorithm trying to do? Well, the jet, the QCD splitting goes from one hard parton to two partons, to daughter partons. The algorithm is trying to invert this process because it starts from two particles and we like to cluster them together to give something more primitive. And so we know that QCD splittings are enhanced in the collinear limit, so where the transfer momentum between these two guys is small. Now, Kt, transfer momentum with respect to the beam, times the azimuth rapidity separation gives you precisely the relative transfer momentum of these two guys. So the Kt algorithm is the one which is most faithful to QCD because it's trying to reproduce, exploiting the singularity structure of QCD matrix element to invert the parton shadow. Unfortunately, it's the one which is also most sensitive to the messy environment of the LHC. So that's why this is usually not used at the LHC. And the Cambridge-Jacques algorithm, which does something similar because it's enhanced in the collinear limit, the angular, it's mostly used. Now, fairly surprising, the one which is the standard choice for the ATLAS and CMS collaboration is p equals -1, which is called the anti-KTI. And this is counterintuitive because there's nothing to do with QCD. What the anti-KT algorithm does, though, is that it tries, the measure goes like 1 over KT. So two particles that are soft for anti-KT are infinitely far apart. And so what the algorithm does is that identifies a hard direction and clusters particles along this hard direction. So anti-KT jets will look like that. So it would look like a hard core surrounded by a cloud of softer particles. Which one do you need? Well, depends what you want to do. If you want to do very general jet studies, then anti-KT is probably a good choice because of it has reduced sensitivity to non-perturbative physics, PILAB, and things like that. If you want to instead go and exploit the underlying structure of jets, so jet substructure, then you will like an algorithm which is more faithful to the QCD splitting pattern. And so maybe Cambridge-Jacques would be a good choice. But, and I'll leave you with this picture, you can try and compare them. And this picture tells you why the anti-KT algorithm is really preferred. You see that the algorithms which are QCD-like, they're also prone, they give rise to jets which are not very round. So this is the plane is azimuth and rapidity, and on the vertical axis I give the PT of the star. You see these, the two at the top, they are the ones which are have the structure which resembles QCD. On the other hand, they're very regular, so they're hard to calibrate and very sensitive to pileup or other soft physics that we don't know how to model very well. On the other hand, the anti-Kt algorithm gives rise to very round jets. And it's not just pleasing for the eyes to see that, but it gives you resilience against these things which are difficult to model. It also makes calculation in resound resolution theory easier, but that's different. Okay, so what I want you to take home from this very brief discussion is that there are a variety. So jets emerge as a useful concept. However, they are not uniquely defined, and for very many reasons. First of all, the resolution at which we want to define jets, for instance, the jet radius, but also the choice that we make to define the distances between the particles that we want to cluster together. This choice, the choice that you can make had consequences on the structure of the jet, on the inner structure of the jet, but also on its resistance against the non-perturbative corrections. So there's not such a thing as the best jet algorithm, but there's a jet algorithm that suits you best. From the point of view of phenomenology. Okay, I think I'm happy with what I was able to tell you. Very general discussion about jets. The notes contain a little bit more of information. I'll put them on Slack later on. And so what we will try to do tomorrow is take one jet and try to study some of the internal properties of this jet. And we'll try and use resound perturbation theory to do so. Okay, I think I'm done.